All right, so let's join.
Hey,
Hello.
hey,
Hello.
how are you? Can you hear me okay? I just turn on. Actually, let me turn
Yeah,
my volume a little bit. Yeah.
I hope you can hear me as well.
Yes, I
Uh,
can.
so, welcome. Let me do a quick introduction. So, this is
Sure.
Mary Grygleski, if I pronounce it right,
You're
right?
glad you got it. Yeah, yeah, no problem. Yeah.
Right. So she's an IBM developer advocate. She has been working with React, mobile, DevOps
Yeah.
space, speaking over 50 conferences and 25 meetups in September. Wow, that's a lot.
Yeah.
So the title of is Thirst-Quenching Streams for Reactive Mind. If I didn't misspell it, that's the
Yeah. Yeah.
section title.
You got
Right,
it.
Mari, you're able to share screen and
Sure.
ready when you are.
Sure. Let me do that and share screen. I have to just pick the right screen. Okay.
Right.
Yeah. Can you see my slides right now? Yeah. I guess let
Yeah,
me run it
yeah.
the presentation mode.
Right. Let's see.
Okay.
Yeah,
You
I think
can.
you just need to make it full screen, like the presentation mode, or
Oh
like
yeah, yeah, sure, sure. Yes.
because I still see the IDE at
Yeah.
the escape probably will show lots of codes.
Yeah.
So I'll give the stage for Mary. Which
Yeah.
one of this?
Mary.
So,
Yeah, that's good.
okay.
Very nice.
We're going to give the stage for Mary, and then after the session, we can have a quick Q&A. So,
Sure.
stage is yours.
Thank you. Thank you very much. Yes, so thank you everybody. I have so many screens. If you don't mind, just 1 minute.
So now,
Yeah,
let me switch here
I
to
do. I,
Mari. Let me see if Mari is ready,
okay. And
and then we can move forward. Yeah, I
okay.
think I think just mute if you are on Pine. I just mute it because there is like a small delay here between there. So
Yeah, I noticed too. So I basically stopped that screen. Just let me make sure on Pine. I just want to see the chat, right? And
right,
then I basically can completely stop the video, so then it doesn't
right.
have sound, right? Okay, that's what I'm doing now. Yeah, I noticed too. I still had that running. So okay, yep.
All right.
Okay, I
So
think I should be good. Yeah, I know it's kind of somewhat confusing, but thank you. Yeah, I have many screens running, so yeah. All right, am I in the show?
yeah, you're right. You're right. So go on. The stage is yours.
Okay, so I am on the show, right? Yeah. Okay. Yeah, so thank you everybody for joining this session. Again, my title is Thirst-Quenching Streams for the Reactive Mind. And essentially, what I wanted to achieve is really compare reactive streams implementations. And actually, the time that when I submitted this proposal to the time now, in between, I've done multiple things, meaning, well, I also actually run a live coding stream on Twitch, and I've been actually working on some Vertex project, which I will be doing a bit of demonstration in here too, just to share with you. Won't be able to do everything, but some highlighting some things for you. And presumably too, I think this track is like for introduction kind of material. So I may actually get into some of the basics too of reactive programming, reactive systems, and reactive streams, rather than going like way too deep into anything. I mean, as such, I only get 1 hour too, but I like to really highlight something so then it's going to make some sense to you, particularly if you are new to reactive programming, reactive systems, and in this space event-driven, for example. So as such, event-driven, asynchronous, reactive seems to be like all meshed together. We talk about these all the time. And to me, when I first started promoting this about a year and a half or so ago, when I joined IBM, even I was kind of finding it very confusing because there is also React Native, and of course those are JavaScript framework. React and React Native is actually the mobile for React. So I'm not talking about JavaScript right now. Now, there are concepts in those libraries and their language framework that supports reactive concept. And that's what I'm going to focus on. And plus, this is also a Java conference, and also my advocacy is in Java. So I'm kind of primarily focusing on, on the libraries and support. All those are focusing on Java. But some of the concepts, though, they are applicable to any language or framework or libraries. So they're no different. So I just want to point out, sometimes we tend to like to say, well, this is React, this is reactive, all these things. It's just, no, let's try to figure out, the problem we are trying to solve. And we're using the reactive approach. And so that's what we're trying to like get into. And as such, today I kind of talk a bit more about reactive streams, but at the same time too, I will be bringing up the reactive programming and some of the basic fundamental concepts. So if you actually have some questions too, or if you find it kind of not, relevant, also try to let me know in the chat. Then I can also make sure I am talking about things that matter to you. And again, thank you so much for coming. I see a lot of you. So, okay, so I've been talking enough about myself. And I'm a developer advocate at IBM, and I've been with IBM for almost 2 years now. And my area is in Java and also open source. We're very much IBM. We're all open source these days. We participate too as committers, as program managers, as like advocacy, all these things we are kind of promoting, in this area, open source, and also for Java. And as you know too, if some of you are working with enterprise Java, especially in Jakarta EE, all those, and we are very heavily also helping to build up the ecosystem. So, and I'm specifically in more of the event-driven architecture and also like reactive systems. So that's me. So just again, let's start off with some basic concepts. So reactive programming, reactive systems, and reactive streams, these are not exactly the same. So I like to do some distinction about these. So reactive programming, essentially, it makes use of the functional style of programming in Java. And as we all know, Java 8 started coming out with lambdas, with streams processing, all these functional style of programming, and essentially time was ripe to introduce like more reactive functionality into the language and the framework and everything. And so as such, reactive programming is achieved through the use of like functional style of programming. And even functional style of programming isn't completely the same as reactive programming. Now, here's some just fundamental differences. Functional programming as such is still, we're dealing with, the flow of your program is driven by, your thread of execution in your code. You're doing some commands, some kind of imperative style too of commands, and it flows, your thread flows. So that's how it drives the program flow. But for reactive programming, we're dealing with more of the data that's moving through your system. So it's really like streams of data that we're handling with. So when the state of these data essentially get transformed, and that's what is driving the flow of this system. So this kind of like subtle differences. And then reactive systems is a bit like a level beyond. Because reactive programming, we're essentially the fundamental like mechanics of what like enables your program to work, a microservices ecosystem in which you have a component. So you're applying reactive programming style to write that code, and that is handled using reactive style, essentially declarative style and not imperative. And you might have heard of imperative versus declarative. And interestingly, I've been kind of thinking about it like how, as human beings, we function very much, in a reactive way, meaning that when we do things, we just say something and we need something, we just say it, and then we go and do something else while we are waiting for what we're trying to get, right? So that's actually, if you think about it, it's very, in a computing sense, it's very reactive in that sense, because we're expecting I had actually an original talk that I did last year, was more introductory. I call it reactive for the impatient, because we are really impatient people. We don't want to wait. We want things to happen right now for us. And in some cases, we are so impatient that we actually want it yesterday, right? So, but that's the idea. Reactive, programming itself is enabling that, and also very declarative, the style of programming. And whereas, what we learn though in computing, and that's what I was trying to bring up, is that in the computer world, when we first all learn programming, we actually are all learning the imperative style. everything is kind of blocking. So when we issue a call, like some statement, right, we'll just say system, some kind of like read line. So that's a blocking call because it's waiting for IO, right, input output to come. So that's really imperative. And then when something happens, then we go to do the next thing. But think about it, right? In a computer sense, even that is actually very impatient. Well, I should say very inefficient, because you're holding up a thread. Your thread is doing something and then it's waiting for something. So it's holding up things. So on a hardware level, right, we're talking about processors. What it used to be was that hardware used to be, single processor, single core. That was easy, because then on the software level, then all we need to do is just single thread, it doesn't matter. And it's the operating system that does, maybe like you have thread and you can kind of do some context switching if you're doing multi-thread programming. However, if you think about why, reactive, and now kind of talks about reactive systems that's becoming more popular, I'd say in the 2010s, in that time range. So in the past decade, started to come out because the hardware is really ripe. Right now, hardware, we have multi-core machines, we have multi-CPU, we have containerization, virtualization, all of these things that are happening that is also enabling cloud, all of these clusters that can run things you can run on the cloud, and you have once physical machines, but it actually is supporting so many virtual machines inside. So all of these things are really pushing the limits, of also software needs to get caught up. So that's when like reactive systems comes into play. So reactive systems, really, what we're talking about is really systems that we're working with, as a whole in an ecosystem. We're not only dealing with one component, one thing. We're really participating in an ecosystem in which we all need to, like, essentially be synchronized with one another. Even though within us, things are not done being synchronously, not blocking, but in some ways too, on that level, reactive systems too, what it's trying to achieve is really like concurrency distributed system. We're living really in reality, it's very distributed. Everybody, we do our own thing. We come together when we need to, kind of thing, and we need some information from someone. So that would have to happen. So long story short, I kind of explained too long, and it's basically, that's really the reactive systems that we are referring to. So with, reactive programming, why is it kind of better is, some people have asked me too, like in my last year, especially when I was doing talks about that, they said, well, right now, we can add hardware to some cluster and they will handle things. True, you can do that, right, in a cluster. But the thing is, we want to make use of software. So the difference is that it used to be like if you're doing hardware, then you would still need the hardware to take care of things, they each manage the thread. But the thing is, for software, then we essentially are moving the processing a lot more into user space. And so then it used to be, right, if that you have your thread running in the kernel, in the OS level, then there would be a lot of context switching, right, if you don't manage that threading well. But now with reactive programming, what is actually good with reactive systems is that it's actually moving all of these threading, all of these being handled in the user space. So in other words, then you relieve like the OS kernel from having had to manage all of these threads. So, expensively, as we all know, IO is very expensive. Your operating system can be overloaded. So that's why we want to have reactive systems. And as such, too, reactive systems also is very like event-driven in nature as well, as we all know. Events happen, and then we need to handle it, kind of a responsive type of way of computing. Okay, so now let's then move to reactive streams. That's my talk. And the reactive streams really is an initiative, and now actually became a specification. And it's an initiative that's essentially is now there's a new foundation that's formed called Reactive Foundation, and it comes out of the Linux Foundation. So Reactive Foundation is the ones that kind of governing the reactive stream specification. It first came out when Java 9 came out because the Flowable API also is the one that essentially reactive streams is built upon. Okay, so that's a bit of that introduction and took me like 10, 12 minutes. So now let's kind of go back a little bit because some of you too, I'm sure you're also doing programming, right? So you're saying that, well, all these kind of things, kind of abstract to me, like all these systems. I'm not dealing with the systems level yet. I'm like I'm just newly coming into this field. I want to know how to do programming. So this is why I thought, let me also talk about this on the programming level. How do we start, right? So now there's this RX, which I'm like borrowing from this different illustration. I think is a real good way to learn. Because reactive programming, what we're essentially dealing with are really streams of data, no longer like a structure in which we define, your structure, you have, data, kind of all these types and all that. Essentially, reactive programming, we're dealing with streams of data. So the RX Reactive Extension, which actually came out of Microsoft in 2010, and then Netflix ported it to Java. So that's how RX Java was born, if you're working with RX Java. So a bit of background. But anyway, the Reactive Extension, they actually have a website that actually talks about Reactive Extension streams programming, and marble diagram is a good way of learning. So essentially, we're dealing with streams of data. So we represent the streams as like a line up here. And then all of these different shapes in here, they are events that comes in and carries with it some data. And over here, this one for perpendicular one is essentially telling, indicating that the stream has terminated. So maybe we program it just so the stream only expects certain amount of data or time that it receives some data, and then it terminates. And this one, the third one, is interesting. Why is it I highlighted in red is because this X, it represents an error event. So even event that, event comes in, there's no distinction, it's just some event. So it's up to the, whoever is interested in processing these events, the consumer side, they will need to handle if it is an X meaning an error. So essentially, there are no, it's error events it's not second-class citizen. They are the same, being treated the same. And then the bottom one here is essentially just an open-ended stream. A stream can be like there, sitting in there and expecting data to come in. There's no, end to it. Okay, let me go back and let me see. Okay. Now, some example of like RX marble diagram of, you're saying that, well, then how do I actually operate on these data? So the thing to do is that I'm sure if you are doing RX Java, doing Spring Reactor, there are a bunch of like operators too that we call it like we operate on the stream. So these operators are what transforms the data that comes in from the stream. So this is a very basic example of the usage of map. So map essentially transform. And thinking functional style, just like us, if you remember doing like math functions, we just like pass in some formula and then it transforms the data. You have some input and it comes out output. So essentially that's what map is doing. You basically just do a map and pass in that formula. In this case, this example is just multiplied by 10. So you see that it's represented on this streams, the timeline. So this is like the streams coming in and essentially carrying with it 1, 2, and 3. And what will come out of it, the result of it, you'll see will be a 10, 20, and 30. The data will get transformed like that. So when it translates to code using RX Java, it will be observable.just. This takes in the input, and you operate on it, apply a mapping transformation function to it. Then it's multiplied by 10. Immediately, too, then you do a subscribe. .subscribe is consumed it. And the consumer over here, this example will be using Timber. That library to just print it out to the console. So that's what it is. And so you see output of item 10, item 20, and item 30. And if you're interested in this more too, especially on the reactive programming side, rxmarbles.com has a lot of good materials that you can look up to. And you can try things interactively. There are other mapping, I shouldn't say mapping, there's also transformation type of operators such as filter. Filters will be very useful, especially if you're processing like big sets of data. You essentially, these are streams of data coming in, and you can actually use, in Java, you use the composite style of chaining up all your calls. You can actually have one single statement. You take in the input and apply a filter to it. For example, employees data, you can say, well, only return me like employees have worked here for 10 years or something. And so you can kind of do that quite efficiently on the programming level. So yeah, have a look at that when you get a chance. Okay, so that was just a bit of a sidetrack into doing programming. And now kind of let's address some of the problems that reactive systems are trying to solve. Will be like concurrency and parallelism type of problem. Yeah, these are the major things I'd say. Of course, too, they're not just, while coming out of a concurrency kind of situation, then you obviously have many things, right? Because we're worrying about performance. Is it responsive? How about like error? Then essentially too, reactive style, you have to also handle error situation and being very resilient. And also like the scalability too, right? If you have more requests coming in, you want the system to be very resilient, able to like grow in number of processors to handle it, things like that. So anyway, fundamentally, we're trying to address problems of concurrency. So concurrency is essentially dealing with multiple tasks all at once. That's concurrent. Whereas parallel is basically doing multiple tasks like all at once. Yeah, so there's a bit of a difference. In parallel processing, it's always we're referring to like having hardware, having multi-core machine. So these days too, even in our MacBook, I'm running this, I have 2 cores, so it's not just like 1 core. So that's kind of parallelism. This can be achieved through having multi-core hardware. So these are problems we're trying to solve with reactive systems. And of course, too, I don't think I actually even mentioned is earlier. I should have mentioned, which I actually have a link, is that reactive systems, what we are trying to also this reactive, there's a reactive manifesto too. Let me kind of quickly bring up a diagram, and I apologize. I thought I had it, but I do have it in another diagram. So I'll just kind of quickly pop this one in here. Just so it's clear to everybody too. I'm just having like multiple things. So let me kind of just do this like quickly if you can see. So reactive systems has this guiding principle to it. It's basically the reactive manifesto. So I want to bring this up because that's what kind of differentiate between if a system is qualified as reactive or not. You can also have Kafka too. Kafka streams, they also handle some of the reactive side of things. But even with that, I myself am also doing a bit of kind of research into, let's see how exactly they differ. So it doesn't quite qualify exactly as reactive, but it does support like reactive processing. But so essentially, we do want to have the 4 principles. One is being responsive. Your reactive system is very responsive. There's not much wait. The wait time should be very little. And then you need the system to be very resilient. If there's any error that occurs, it needs to have some way of fixing itself, right? And all that stuff. And then there's also elasticity, which I also mentioned in a case in which you get too many requests coming in, you want the system to be very resilient, or I should say, well, I use the same word, very elastic, very scalable is the word to use. So then, you get more, for example, I think if like a company doing e-commerce, flowers.com, around Valentine's Day, you have tons of, requests coming in. So you want the system, the order processing to be highly efficient. You want to immediately know that, well, that right before Valentine's Day, I'm going to receive 1,000 times more orders than normal time. So then I want to be able to spin off all of these processes to handle all of these orders accordingly. Not just like, orders too. There are also things that, your whole processing needs to essentially like grow, in like magnitude to handle all of these volumes that comes in. So reactive kind of address that kind of aspect of a system. And then with all of these two, they are being enabled. How is it being enabled? Is really through message-driven capability on your systems. So we'll also kind of take a look into the what message-driven means in a little bit, but let's kind of come back here. So I just want to kind of go back to the reactive streams. I'm sorry if I'm like jumping around. I kind of get somewhat like excited talking about these things too. So okay, let's say, right, we're talking about reactive streams. These are streams of data coming in. I bet a lot of us too wouldn't even think too much of it. However, there's a bit of a subtlety that I feel we should all be aware of. There are differences in how you process the streams. There's a model that's called push, and then also another one is called pull. So essentially, there's push or pull. So it kind of seems like, okay, you may be thinking, oh, so it's basic enough. We know you can push or pull. And what it means is that the push is essentially, you have like streams of data coming in. There's a push, you push the data. So upstream will actually push the data to downstream. And then in a pull model will be downstream is the one responsible for pulling the data from upstream. So in other words, the upstream the publisher doesn't really send the data until like somebody, consumer, is interested in it that will actually pull it. So that's what it is. So let me kind of illustrate a little more using this diagram. So in any kind of event-driven type of systems, streams processing, kind of message-driven messaging systems, we're dealing with data that comes in as stream. So we always have to have someone that the source, or we also call it producer, or there's also publisher, in the, especially in messaging systems such as the old Java messaging system, JMS. So that actually we call those like publisher as producer because it produces the data. So in this case too, in a reactive kind of context, we're talking about this producer or publisher will emits the data. So something happens, it starts to send some events, it sends out the data, emits data. And over here, it will basically sends it out without asking explicitly. It's going to actually push the data from upstream to downstream. Now, there are different kinds too. Let's say in JMS too, if you're familiar with it, there are topics, it's more like you have to subscribe. So essentially, there will be consumer that, that we need the data. So, but we don't need everything. We only subscribe to what we want. So that's kind of like topic way of doing things. And there's also the queuing way of doing things, right? You can have data that keeps emitting and it kind of builds up a queue, and it's up to whoever is interested can go and fetch those data from the queue. So that's kind of the primary way of how stream processing kind of goes. And there's that push in this case. Then there's also pull. Like again, if in the consumer side, if I'm interested in some data, I basically will kind of signal to the producer and says, I need some data. So that, when the producer receives this kind of request coming from the consumer, then when it comes time to emit data, then it will send the data over. So that's also some interesting thing too in this type of processing is that your consumer can be subscribing to some event that hasn't happened yet. So it's basically too is that there's built-in, it should be in any library, it should also have like built-in capability in which it allows, me, if I'm interested in something, I subscribe to it before the data happens. So then, it's registered somewhere in which when the producer, it's, things of interest to the consumer is happening, started having data, then basically it knows that, okay, well, if, Gary needs that, then I will send it over there, right? Kind of only send it when it's being pulled. Now, there's also, interestingly, this kind of model, too, is also being described as like pull, then push, too. And essentially, that's what I think the reactive streams, a lot of the implementers are doing. Their style is doing like a pull and then push kind of style. Now, when I go back previously, that push, there's actually one library that's actually doing a more like a pure push kind of model. And that one is the OSGI. If you're familiar with it, the OSGI actually they have a push specification, and they are doing kind of a pure push way of doing sending data on the streams, like a push model. But I'll also touch upon that in a little bit. Okay, so now going back a bit too into like reactive streams, what are we trying to achieve, right? So the reactive streams specification that's currently managed by the Reactive Foundation is composed of 6 companies, or 5 of them now. And essentially, what we're dealing with, we want to handle back pressure. So it's just a note on back pressure is that, simple enough, right? We were talking about streams that travels down, and in the normal circumstances, like an e-commerce system, for example, like you can have normal traffic. We don't need to spin up a 10,000 servers to service thing, and it's in normal time. Just leave 2 running. So make sure maybe, their orders coming in on an ordinary day is not more than 100 per day. That's easy. However, times come in which you all of a sudden have like many, right before Valentine's Day, this flower shop will receive like 10,000 or thousands more of order. Then back pressure can build up. You have over here, I'm using these shower heads, as all the water spraying on somebody trying to running toward it. And what happened is that, this back pressure is kind of borrowing from physics, from mechanical kind of physics, right? It's essentially too that, you have too much like gas, right, coming in and at you, or water coming at you. Then essentially too, this stream will essentially, instead of flowing in the direction that it's supposed to flowing to, it will actually be pushed back. And so then that's what back pressure means. So, and today too, all of these reactive streams, what it's trying to address is that, all of these implementers of reactive streams, they do need to have mechanism to handle back pressure. That's one of the primary kind of importance of this specification. But I, again, just wanted to point this out too. And this is just another picture I saw. I believe it's okay for me to take it. I couldn't find who actually is from, but I wanted to show, because I think it's really funny too, in which, you get like shower, your water pushing at someone and your subscriber trying to do it, and I just can't handle it. And actually, let me also give an example too, if I have a minute. I was actually at a conference in North Carolina last year called All Things Open. If you are there in North Carolina, All Things Open, a very wonderful open source conference. They had like 5,000 people, and then they were, treating us all to like for an after-hour drink. Oh, there were only 2 bartenders. So as you can imagine, the line was 500 people for 2 bartenders. So immediately I thought of myself, oh, that's back pressure. You get a lot of consumer, or in this case, it's interesting. You think of us wanting to be served your drinks, as the kind of, all these demands, requests coming in, and they come into the consumer, which is actually, in this case, you have to kind of twist it a little bit. Think of the bartender as the one servicing you. They need to address all of these things. They just can't handle it. So that would be another example of back pressure. Okay, quickly, let me kind of also then talking about to a bit more, real thing. So essentially, reactive streams, it's a specification. It doesn't have any implementation itself, meaning that it's just a specification, essentially a guiding principle, right? So then it actually has like 4 interfaces that it has. Is publisher, and in the publisher there essentially is the publisher will have a method that's subscribe, and then there's also subscriber, and it's basically subscriber is the one that will be like you have to specify, right, on subscribe, on next, on error, and complete. So essentially too, the subscriber will be the one that kind of takes care of the subscription too, in this case. And then over here too, you see that there's subscription. Now subscription actually is the one where the back pressure is being applied over here. Handle over here is in the request side. So a subscription essentially kind of signifies that, it materializes a situation in which there's publisher and subscriber kind of forming that relationship in there. And there's like requests that being handled by this subscription accordingly, and back pressure is being handled there. And then there's also like processor, in which processor essentially is like processing each of these entities in here. But okay, let's take a bit closer look too in Java interfaces, how it gets translated to code. So the interface this is how it looks like, publisher, and has one method of subscribe. Subscriber has on subscribe, on next, on error, on complete. And again, just a repeat, but just wanted to show you in code. So subscription has request and cancel, and back pressure supports what happened there. And then the processor, essentially processor extends the subscriber and publisher too, and it will do the processing, handles all the processing. Okay, let's get a bit then now into the reactive stream side. Reactive streams, and this, in code way in the package is org.reactive streams API. And there are only specifications and no implementations, which means that if you want to use reactive streams, you will have to implement your own libraries for it, and then just follow the interface. Now, and that's what I like to also point out, is that reactive streams is not something, if you are, working with applications, you're building applications, you probably don't want to deal with this kind of it's a bit more primitive way of, handling publisher, subscriber, processor, and subscription. You usually would rely on libraries. So here are the ones that I've listed out, and these are in the Java world. These are like the major players currently that have implemented reactive streams that I would suggest that you look into if you're interested, and if you haven't looked into it yet. And I'm sure maybe some of you are already working with this too. And again, they, in order to have a proper specification and is kind of got a foundation that's guiding it, it needs to have the TCK, right? The compatibility kit to it, or test compatibility kit. So essentially, if any implementers, vendors trying to implement this, they need to pass the test that's specified in this TCK in order to qualify them as conforming to reactive streams. And basically, the idea is managing back pressure, also managing like asynchronous processing of streams, And the one nice thing about it is having a specification like that is that you can actually allow for interoperability between implementations of libraries between, these different vendors too. So in other words, you can actually, and that's something, and by the way too, if you're interested, I will be actually doing or I plan to doing this one stream on my Twitch. So many words of stream, we're overloading here. But I'm actually also doing the live coding on Twitch. And at one point, I want to illustrate an example of building like different implementations, using the different vendors implementation and build up different components and essentially chain them up. So then I have one that's implemented using Vertex, the other using Arca streams and microprofile, and basically chain them together and see how they work. So if you're ever interested, feel free to follow me, and then I should have it in one of my future Twitch streams to illustrate that. So, okay, so let me then go quickly too before I get into examples. I'm being careful with the time. So again, Spring Reactor, I just want to highlight a little bit. That comes from Project Reactor. It's from Pivotal. And it has the Reactor core. That's the one that, the library you want to use. And if you hear of Spring Reactor, Reactive 2, you have heard of WebFlux, and also like then WebFlux, well, essentially Flux is how they handle streams. Like you can have 0 or n items in the stream. That's what Flux is. And I believe there's another speaker in here when I was looking through the program that she'll be talking about more on the WebFlux. I think, she'll be able to give you a lot more deeper information than I'd be able to do now. But again, just wanted to point out, so mono, there's basically mono handle either 0 to 1 item on a stream. So yeah, again, with Project Reactor too, I just want to also point out, now you notice that in my previous screen, I actually have Spring Reactor and Reactive Extension together, the RxJava. The reason is that RxJava and Spring Reactor, these are all open source libraries. The core engineering teams, they work on both. So then you'll find that their operators that operates on streams are very, very similar. David Connaught, who is based in Europe, and he's wonderful, and he's the one that's kind of leading this design. And so that's why too I kind of grouped them together, because they're very close to each other. Now, the nice thing, I think there are also people asking me what library should they use. I think if you are a Spring shop, you may find that using Spring Reactor might be somewhat easier. Well, it's probably naturally easier because the Spring Reactor is already kind of built off of leveraging on all of the Spring framework and all that. So that would be one thing. And of course, it also has interoperability too. You basically can build up your pipeline using different things. And basically, if it conforms to the reactive streams, you can have them all kind of strung together. It shouldn't be, theoretically at least, it shouldn't be that, hard to do, or it should be possible. We have yet to do it, so I'm hoping to show that at some point. So, okay, so back to now with RxJava. RxJava, and let me also point out again, RxJava and Spring Reactor in my mind too even, I don't feel as much of them as, as much of a systems level type of functionality. I mean, they do great, on the programming level because of all of the operations you can do, operate on your data. It's just so that their focus is less on system as a whole. Because if you think about it, if you want to satisfy that for reactive manifesto, then by itself, you can't just use their library and start building, okay, responsive, being like resilient, elastic. And very often in today's world, in the cloud, in containers, we leverage on like a cloud native environment to actually enable them to run. So by themselves, they are less of a reactive systems kind of library. They are more, kind of catered for you so you can build up reactive components, let's put it that way. Now, RxJava, just one note to note is that RxJava is currently on RxJava 3. And the thing is, though, is still RxJava 2 is more prevalent. It came out since Java in Java 8. So before that, it came out from Java 6. So back then, there was actually no back pressure support. So if you use RxJava 2, then it starts to have flowables. Flowables is the one to use because it has back pressure support. If you're still using RxJava 1, then you'll be using Observables don't have back pressure support in their version. But I believe it has like retrofitted at this point. But anyway, if you're using in version 2, use Flowables. Okay, so now let's kind of move on to Vertex. And Vertex, I'll be demonstrating a few things too. As such, I've been starting to get deeper into it. I want to point out, because it's pretty amazing framework in the sense that it's not too complicated to use. And in fact, you'll see some beauty of it. It leveraged on a model called Verticals. And for Verticals model, essentially what it does, it enables you to do the deployment a lot more smoothly, shall I say. You don't necessarily have to write Vertex and basically extend the abstract vertical too. It's optional. But if you do that, then you can essentially leverage on the framework to work with the Vertex event bus. Now, Vertex has a very, very cool concept. It's simple enough. It has its own event bus. So I think because of that, it actually is built very well and to be very flexible, because you can actually mix and match even different language libraries and languages frameworks. So Vertex is also not just for Java. It's also for JavaScript, for Python, for Scala, for all of the other major languages. And I think the older version actually also support PHP too, for example. So I think if you have some like older systems, right, you're trying to like retrofit it into like an event-driven kind of system, I think you should investigate into using Vertex because it really is very flexible. And not only that, here I didn't say it, it's actually the core engine that enables the reactive capability in Quarkus too. I saw that some of you are talking about Quarkus, especially I think Eric talked about Quarkus in his talk. And I think the previous speaker, I think also talk a bit, if I remember, also talk about Quarkus. So a couple of speakers too. So if you kind of open up the hood and look at it, it's essentially Vertex that's underneath the event-driven model that enables Quarkus to be so fast. Is because of the reactive capability that it is leveraging on through the use of Vertex. Now, there's also another library too called SmallRye that is actually an effort that comes out of also Vertex, that group of engineers. And also just a note too, is an Eclipse project, but they're primarily being shall I say, more like driven or kind of the committers, the contributed by like Red Hat engineers. So now IBM is part of, we're kind of with Red Hat. So that's why too, we're also trying to kind of work with them too, to also kind of highlight. And in fact too, I mean, even let's say I don't work here, I would still look into Vertex because I'm finding it to be really, truly fun to be writing program with that. So I will illustrate to you, and I'm trying to be cognizant of the time. I tend to talk too long. So let's move on to the next thing. So, and one thing is that I forgot to say, Vertex also have integration with Reactive Streams too. And it's interesting, but then if you find the documentation, is a bit kind of not as much information on the Reactive Stream side. But then it's the nice thing about Vertex is that you can always combine with other, kind of libraries. For example, MicroProfile, I'll be talking about it. You can basically plug in your Vertex event bus and all that, and try to build your system that way to leverage on that. So to sum up too, we probably don't want to say one thing is better than the other. We need to identify what each thing is good for and see how we can kind of combine them. In a reactive world, that's actually great because everything is all, not tightly coupled. How nice it is. We're living in a world that, we are like full of different ways of doing things. How about if we all collaborate and make things work all in our own ways, but we can talk. So anyway, that's just some thoughts I have. Okay, so let me go into Arca Streams. So Arca Streams come out of Lightband. Lightband used to be called TypeSafe, the company that invented Scala by Martin Odersky, as you probably know. So Arca, I have to say, IBM originally had a partnership with them, but unfortunately, we did not renew it this year. It's supposed to expire, or actually expire, I should say, but we did not renew it now. However, I wanted to say that I did work a bit on Arca, so I brought it up here. Arca Streams is an Arca framework. The Play framework, which is dealing with front end, is very powerful because the design, it's very sophisticated. However, that sophistication is not easy to learn. If you're first coming to it, you'll be like, what? Kind of scratching your head. Don't feel bad. I think everybody encountered the same. But if you spend enough time on it, you'll realize the beauty of it. It really, truly is very sophisticated. Okay, so without saying that, let's take a look Arca streams. So in the reactive streams kind of context, Arca streams too, they implement the reactive streams interfaces, but they kind of interesting. They are kind of, I've always looked at them like they are kind of like the gods or something. I mean, they're very sophisticated folks and they're smart engineer. I mean, everybody is smart too, but they have a different way of doing things. So they completely decouple from the reactive streams interfaces. So, and basically, they are, they're an implementation detail. They deal with their own detail of how to pass stream data between individual operators. So over here, I didn't say, but essentially, they have concepts of like a sink, and the sink, and then also the source, and then the source is where the data comes out of, and then essentially the sink will be where you gather, all your data in transit and all those things. And basically, it also has a flow too. So it actually uses its own way of doing things. But yes, underneath, they do support the reactive streams specification. Now, their goal is that they want to design an API that's minimal and consistent. They want to have like explicitness over magic and compositionality. So combine like pieces and retaining functionality of each part. They are truly like quite good, into doing that level of computing and, on the software level. And they actually also provide tooling to handle stream processing, like back pressure, buffering, and all those things too. So they do have their own way of doing things, but they are definitely very sophisticated kind of library. Okay, so now let's take a look too. There's also microprofile. Microprofile also was also mentioned by Eric, I believe, and other speakers. And essentially too, it has a special focus. It's basically come out of more of the Java EE kind of camp. It's now currently in Eclipse project, and it has a primary focus is really on microservices and enabling enterprise Java to be built more efficiently. And it has some special focus for microservices types of application and serverless type of scenarios. So they have their own special kind of use too. Less of a full stack kind of feel to it, but nonetheless, very useful. And I myself actually starting to get involved with the microprofile working group at the Eclipse Foundation. So that's why I start to know more too. Now, essentially too, in like all other reactive streams, reactive systems, and we want to have location transparency and temporal decoupling. And so again, decoupling everything. So then it's not so much hard coding things, and everything dynamic lookup and all that. And one note to point out is that it integrates very well with OpenLiberty. If you are a WebSphere, IBM WebSphere, the app server, if you're familiar with that, the open source version of WebSphere is OpenLiberty. And it's actually even better because it's lighter weight than the previous, like Java J2EE, in the 90s or early 2000, right, with WebSphere, J2EE. Now it's all JEE, but OpenLiberty is what it is. So microprofile has a good kind of support for that integration. And here, just something extra for you to know too is that in microprofile reactive messaging, the application beans will contain methods with annotations, like annotation of incoming and outgoing, and they are connected by name channels too. So the channel is really a name indicating which source or destination of messages is used. So channels are really opaque strings, so you can see. Then that's what it enables all the location transparency. And they are really, these, match up by channel name. So over here, for example, outgoing, you can label, in order. And incoming and outgoing are the ones that handle the incoming as well as, both kind of directional. And then, all these things, as you can see, I mean, this is just a diagram to illustrate that. So I can talk more later too, like outside of this. So let me move on to, okay. So one more thing is I like to talk about, see, I'm kind of so excited and I'm actually filling in this hour with so much information. I think I can keep going too for a long time, but for now, let me be quick now. So RSocket, now some of you may have heard of that. RSocket, it stands for Reactive Socket. It's actually, interestingly, it's a binary protocol for use on byte stream transports. So it's a bit more primitive, lower level. And it's aimed for like level, you look into the 7 layers of network, kind of network processing. So they are on the more layer 5 and 6, right? The transport and the application layer. And so essentially too, it's highly efficient, and there are 4 models too. It actually, the nice thing about this is the channel one's interesting because you can have, like, the channel have bidirectional. You can have request response, and basically you can keep that open too, and they can, like, the request data can travel in either direction. Then it also supports like the normal request and response, like one-to-one type of relationship, and also fire and forget, kind of like one request and maybe doesn't expect a response. And then also one request and multiple response coming back as a stream. But the channel, again, you have multiple to multiple bidirectional. So now, without going into much detail, let me kind of show you this example, this slides too, which actually came from Spring One platform. They had the conference, I think, last year for. So I asked you for permission to show this. So again, the Reactive Foundation and RSocket. Reactive Foundation also has a strong support for the RSocket, and RSockets also implement Reactive Streams very well too. And it's much faster than HTTP, and it uses much less resources. Recently, is about, I think, a month or 2 ago, the RSocket came out with version 1.0. They're still got a long ways to go because it's still relatively new, and it handles back pressure really well, flow control, all these things. And basically, it's not just for one type of protocol. You can do HTTP, you can do TCP, and you can also have, I think there's Aeron too. So it's targeted for multiple languages, multiple protocol too. And these are the companies that are founders for the Reactive Foundation, which included like Pivotal, Facebook, Alibaba, Netify. Unfortunately, I found out they are no longer in business, and Lightband is there, and Vlingo too. So, okay, some additional info. So you might say, well, do we really need to, do streams? Do we really need to implement reactive streams? You don't really have to. So OSGI, which I mentioned earlier, is an example of one that uses the published streams. It has the push stream R7 currently, and it's a self-implementing API. That's the package it has. And the nice thing about PushStream is that you can actually use it outside of OSGI too. So if you have a need and you want to investigate into other options, you can also check this out. And OSGI is also, my group, we have committers working on OSGI. So I like to also bring this up because I find it to be very interesting. And I also did a talk for this too at the EclipseCon conference last year in Europe too. So there's no dependency on the rest of OSGI specifications and frameworks except for OSGI promise. So it works very well, and it does rely on the OSGI promise too. For, as you know, when you deal with asynchronous, like complete Java complete, all of these future and all those, and you do need to have like promise objects that handle data that will come in the future, kind of thing. So quick thing, reactive primitives. Just a quick comparison. So push streams will use push event source for publisher and push event consumer for subscriber. And interestingly, push streams has an auto-closable, whereas reactive streams, you cannot actually control whether your streams to be closed or not. But push streams, you can code it so then you can actually explicitly close the stream. And then there's also processor, which push streams has this push stream kind of method, and it implements its own API. Okay, so now I think I only have 8 minutes left, and that's kind of my fault. I keep talking, but I didn't even look at if anybody has questions, but I will answer you, I think, if you have questions outside of this, because I do need to get to this, the part of the my demonstration quickly. And okay, so this one it's just a quick example, but I won't have time to go through all of it, and I will make this available. It's actually on my GitHub as well, but I'll tidy some things up. So this one make use of an Akka stream, and essentially what I'm trying to do is a CSV. Let me tell you quickly, CSV processor. So this one too, it reads something from the configuration file, and essentially too, it watches a directory. So over here. This is how I configure it. So let's take a look at the my application config. And so my config will say I'm watching this directory in /temp called data. So any movement in that file directory that's in that folder, I will do something. So let's see. All right. So basically implementing using Akka streams to do it. I wanted to kind of quickly show, make sure I have it. And So I just wanted to show too. So in Akka, it has a thing called flow. And so basically we build up the paths. So we essentially take the path and we create a flow to it. And so over here, we essentially will filter out, if it is a CSV file creation event, then we log this, right? We log this, there's a new file coming in. So essentially you can see, it's quite clean, when you do coding like this, you don't need to like worry about, okay, let me go there and really write your own listener and all that. It has some built-in capability too in here. So essentially too, I wanted to quickly also show that graph. So again, it makes use of the graph too, so of the flow. So this, again, I won't have time, but if you follow me actually on Twitter, on Twitch, maybe at some point I can, let me do this too. And so I just wanted to quickly show you. So I'm so sorry. Here, where is it? Sorry. Okay, here. So this is the part I wanted to show, is that basically if there are new files that comes, then I'm making use of Alpaca. Alpaca is the integration library between Akka streams and also what's happening in the operating system. So this one already has, over here, if I highlight it, it watches a file system directory and streams change events from it. So I'm leveraging on that. So basically, if the new files come, I basically, I create this and it return the source. So it's kind of pretty good, in terms of coding. It doesn't take too long. So, okay, let me quickly then run this and show it to you. So over here, I already have a terminal that opened up. So I could actually run, I don't have to run it command line, but let's do it command line. Okay, and so now it's running. And let me also bring in my, somebody said you can't see the code. Wait, I'm sorry.
It's a little bit smaller, but if you can zoom in a little bit.
Okay, sure.
Just zoom in.
I'm sorry. Yeah, okay, let me do that. Presentation mode, okay.
Just a FYI that you have like 5 minutes, more minutes now.
Oh, okay.
I don't know if you were seeing on chat, but I mean,
yeah.
Since you decided that you're going to have the Q&A afterwards, you can answer the Q&A afterwards.
Okay. Why don't
I mean, the main questions here on the Q&A are related to the architectural. Like, for example, one here is, do you think that everything related to Java is going to switch to Reactive? If Reactive is going to become a programming lane,
that's right.
Yeah, right. Like program programming, like Spring implements MVC. So there are some questions related to that. So, but if you can answer that afterwards on the Q&A,
oh, sure,
that will be great because of time
yeah, that's right. I'm sorry. Yeah, maybe at my Q&A, I can show some of this code too. So I just want to quickly thank you. There are a couple slides too I just want to quickly highlight. This is how you can reach me. This is my Twitter, GitHub, and I will share it again. But these are some of the things I'd like to also invite you to sign up for the Java newsletter at IBM. Actually, if you visit the newsletter link, there are many other things, not just Java. There are AI, Watson, you name it. And this is actually if you want to quickly kind of scan this to get the IBM Cloud sign up, I will actually be demonstrating the Vertex code to deploy it to Kubernetes cluster, and that will be actually running on IBM Cloud too at some point. So I encourage you, if you're interested, sign up for the IBM Cloud. It doesn't cost you anything. You don't need your credit card. Free tier has indefinite time period of usage too, so that's a good thing. Okay,
right.
Okay. And just one thing, this is my Reactive Streams resources, and I can give this to the program manager here. We can share. And also live stream on Twitch is every Wednesday at 12. This is Chicago time, GMT -5. You visit IBM developer channel on twitch.tv. That's where I will be. There are also other IBM developer advocates doing, especially a lot of DevOps, a lot of Kubernetes lately. All of these like OpenShift, if you're interested. So I like to encourage you to join us. And there is also a Reactive Java podcast mini series that I start to do in August. So I'd like to invite you and follow me on Twitter, and I will have more information on that. Then there's also one more thing is the call for code. If you haven't signed up for it this year, don't worry. Next year we'll have it again. It's a very nice kind of for human, for charity purpose, like a hackathon. And there's good prize money too. It's open to everybody in the whole world. So that I like to invite you to also sign up for or check it. And now, with this comes to an end. I think I just have 1 minute left, and I still have the code demo. But thank you so much, and yeah, and I apologize if I kind of go a little bit overboard. But
no, that's great. That's great. So I think the next presenter can ready.
Yes. Yeah, okay. Then you will.
So yeah, but lots of questions related to the programming, like reactive. Everything's going to become reactive in the future. There is one of the Twitch or your Twitch channel that you already divulged on your slides, Mary. Yeah. Also, how does reactive program differ from compatible future? That's one question as well that has. Okay. So some questions related to the programming, the reactive programming paradigm.
Sure.
Then afterward, we can switch to the Q&A chat maybe to answer those.
Yes, I can address those over at the other. Yeah, sure, no problem. Yeah.
All right, that was really great. Thank you, Mary. I learned a lot around reactive. Thank you so much.
Thank you. You guys all have a great day. Thank you so much. Yeah. Okay.
Thank you. Bye.
Bye.